Good afternoon. So in this particular video, we're going to discuss continuous adsorption. So parang part 2 to ng adsorption. So let me share the PowerPoint. Okay, so what we have here is the time, concentration, and height profile of a adsorption column. Okay, so on the x-axis you have the heights, no, or the length of the adsorption column, and then on the y-axis you have C over C sub O. So C is the actual concentration of the sample after passing the column, after passing the height of the column or the length of the specific length of the column, while C sub O is the initial concentration of the sample. So if you want to imagine that, parang halimbawa, if you're going to treat tap water, di ba tap water contains a little amount of organic compounds. So C sub O is the initial concentration of the organic compound. And then as it passes through the adsorption column, the organic compound concentration will be reduced. Okay? So C is the actual concentration of the sample after passing the column. Okay, so generally you expect it to be less than C sub O. And then the adsorption column contains adsorbent. So contain silica gel or activated carbon. Okay, so this curve here, probably you can tell that this shows the portion of column that is filled with after T sub 1, you know, after T sub 1, the portion of the column that is filled with adsorbate. Okay, so after T sub 2 is greater than T sub 1. As you can see, more portion of the column is filled with adsorbate, and so on, you know, and so on. So there will come a time, as you can see from this illustration, generally as the sample goes out of the column, C is approximately equal to 0. Pero there will come a time when C will not be equal to 0. So that's the next concept that this slide is illustrating. There will be a time wherein the C is not equal to 0. So we call that time as the break point. So parang you're going to set a certain concentration CB, and when the concentration of the sample is equal to CB or greater than CB, that would be the break point time. And another important concept is the distraction time. So T6 is the distraction time. So when this concentration of the outgoing solution or sample is the same as the incoming solution, it means that your adsorption column is not working anymore. No? It's not able to reduce the concentration of the solution. So that's the distraction time. So this is the breakpoint time. No? TB or TB is the breakpoint time, and then this is TD or the distraction time. So distraction time is the time that corresponds when the concentration is equal to the C sub O. Okay. Okay, so mathematically, we're going to define the total capacity. Basically, this is the total amount of, or the total time, you know. This corresponds to the total time that you could use the, that you can use the column wherein the concentration of the solution is still decreasing, no? So that's the total capacity. So mathematically, this is the integral from 0 to infinity of 1 minus c over c sub o. So if you will notice, before c sub b, right here, c over c sub o is equal to 0. So the total capacity is just equal to this rectangle. Since the height or c over c sub o is 1, so until this point, this is approximately equal to t sub b. Okay. And then actually after CD or after TD, C over C sub O will be equal to 1. So approximately the area after T sub D is approximately equal to 0. So basically the total capacity is equal to this rectangle plus this curve bounded by this curve, no? Plus the area bounded by this curve. Okay, so what we're going to do, no, in order to approximate this area right here, is we're going to use a triangle to approximate this area. Okay, so we're going to use a triangle to approximate this area. So something like, we're going to approximate this area, this triangle, we're going to approximate this area by using a triangle. So this is the first part, this one, this rectangle here is approximately equal to T sub B. So then we're going to add the area of the triangle. So remember, the area of the triangle is 1/2 base times height. So the area of the base, this one, is TD minus T sub B. So that would be 1/2 TD minus T sub B. And then the height, as you can see, the height is just 1.0. So times 1.0. So this will be the area of the triangle, 1/2 TD minus TB. So the total area or T sub T would be equal to TB, okay, plus 1/2 TD minus TB. So take note that if we're going to simplify this, we're just going to subtract this. This will be negative 1/2 TB to TB. So T sub T would be equal to the average of TB plus TD, okay, divided by 2. So this is the mathematical equation for T sub T that we're going to use. Okay, let's talk about T sub B or the usable capacity. T sub B or the usable capacity is just equal to this rectangle, this rectangle right here. So as you can see, the usable capacity or TU, this triangle right here, this rectangle right here, is approximately equal to TB. So of course, you might see this small area right here. This is the difference, and then as you can see, this is negligible. This area here is negligible compared to the large area of the rectangle. So the usable capacity is approximately equal to T sub B. Okay, so our next equation is the usable capacity. No, that is in terms of time. No, you can say that this is directly proportional to the height of the column. So you might think of this as the longer the column, the longer you can use this. No? So the physical length of the column is directly proportional to the to its capacity in terms of time of usage. No? So that's why we have this equation. HB, that's the usable height right here. HB, that's the usable height, is equals to the usable capacity divided by the total capacity times the total height. So if we're going to transpose this total height on the other side, as you can see, it just means that the ratio of the usable height divided by the total height is equals to the usable capacity divided by the total capacity. So I hope at this point you can distinguish between usable capacity and total capacity. It's basically if you are producing mineral water, so you're not supposed to use the column, no, even though it's still reducing the amount of organics in the tap water. Pero if it's not passing your specification for the concentration of organic, you're not supposed to use the column anymore. So that's the difference between the usable capacity and the total capacity. Okay. So the difference between the total height and the usable height, we call that the unusable height, or HUNB. No, this is the HUNB. So basically, this is HT minus the usable height, and then you have the HUNB, the unusable height. Okay. So if you're planning to scale up the column, if you're planning to scale up the column, it means that if you're planning to produce a column that have a higher capacity, so basically what you're going to do is you need to lengthen the column. You need to produce a longer column, no? So what are the parameters? What are the equations that we're going to assume, no? So the first assumption is the unusable head, whether the column is small or short, is constant. Okay? So you only have one unusable head value for the same operating condition. So HUNB is constant. And then the second assumption is that HB tall divided by TB tall is equals to HB small divided by TB small. So this equation just shows that the capacity, the usable capacity, is directly proportional to the usable height. Okay? So whether the column is small or the column is long, the ratio of the usable height to capacity will be constant. Usable capacity will be constant. So you need to remember those assumption in scaling up. Okay, so at this point, we're going to solve sample problem 12.3-1. A waste stream of alcohol vapor in air from a process was adsorbed by activated carbon particle in a packed bed having a diameter of 4 cm and length of 14 cm, containing 79.2 grams of carbon. The inlet gas stream having a concentration C sub O of 600 ppm and a density of 0.00115 gram per cubic centimeter. It entered the bed at a flow rate of 754 cubic centimeter per second. Data in table 12.3-1 give the concentration of the breakthrough curve. The breakpoint concentration is set at C over C sub O is equal to 0.01. Do as follows. So you need to determine the breakpoint time, that's T sub B. The fraction of total capacity used up to the breakpoint, that would be T sub B divided by T sub T, and the length of the unused bed. So that would be an HUNB. Also determine the saturation loading capacity of the carbon. So the saturation loading capacity of the carbon refers to the amount of alcohol, that will be gram of alcohol per gram of carbon at total capacity. Okay? So basically to solve the breakpoint time, you just try to find this C over C sub O. Okay? This is considered as the breakpoint concentration. So it's in between 3.5. It's in between 3.5 and 4 hours. So just interpolate right here. Okay. Next, in order to find the fraction of total capacity, you need to find T sub T. So in order to find T sub T, remember T sub T is equals to 1/2, or this is just the average of TD plus TB. So you need to find TD first. So in order to find TD, that is when C over C sub O is equals to 1. So you need to extrapolate. Probably if you use the last two data, you use the last two data and then extrapolate for TD. And then take the average, you will have T sub T. And then the fraction is simply TB divided by T sub T. Length of unused bed. So to find the length of unused bed, basically you just multiply the fraction to the total length, which is 14 centimeter, and then you're going to find HB, the usable height. And then the difference between the usable height and the total height will give you HU and B. And then finally, saturation loading capacity, you're going to use the flow rate, the concentration, 600 ppm, the density, okay, the weight of the carbon to solve for saturation loading capacity. Okay, so I'm going to share a whiteboard so that we can solve this problem. Okay, first we're going to interpolate between time is equals to 3.5 3.5 hours, this is in hours, and okay, and 4 hours. Okay, and then C over C sub O, this is 0.002, and then this is 0.03. Okay, so you wanted to find T sub B. So T sub B, this is at C over C sub O is equals to 0.01. So just interpolate. Interpolate between these two values. So you're supposed to get TB using the calculator. TB is equals to 3.64 hours. So this is the answer to the first question. Okay, next we're going to estimate TD. So we're going to interpolate from 6.5 to 6.8 hours. Okay, this is time in hours. C over C sub O at this time is 0.975 and 0.993. Okay. So interpolation, TD is 6.92 hours. Okay. Then let's calculate T sub T. So T sub T is simply equal to TB plus TD divided by 2. So that would be 6.92 plus 3.64 divided by 2. So that would be 5.28 hours, no? Okay. So next, let's calculate the fraction, usable fraction. So the usable fraction is equal to TB divided by T sub T. So that would be 3.64, 5.28 hours. So the usable fraction is approximately 0.689. Next, let's calculate HUNB. So to calculate HUNB, basically, we're going to calculate HB first. So HB is simply HT, total height, times the usable fraction, which is 0.689. Ano? So that would be 14 centimeter times 0.689. You're supposed to get HB. HB would be 9.65 centimeter. So in order to calculate HUNB, the unusable height, this is simply the difference between the total height and the usable height. Okay? So this would be 14 centimeter minus 9.65 centimeter. So HUNB is approximately 4.35 centimeter. So I hope you get this this calculation. Actually it's quite simple. Basically it's ratio and proportion. The longer the length or the height of the column, the longer the usable capacity and the total capacity. And then just try to remember that the unusable height, whether the column is short or long, will be constant. Okay, so we're going to calculate the saturation loading capacity. So I'm going to clear this. I'm going to clear this whiteboard. Okay. So the saturation loading capacity, basically this is the grams of alcohol, no, per gram of activated carbon or adsorbent. So in order to find this, yung grams of carbon is given to be 79.2, no? 79.2. On the other hand, the gram of alcohol, you're going to get this from the volumetric flow rate of air. Then use the density to convert this to mass flow rate. And then use the concentration, the parts per million, to convert this to grams alcohol. And then finally, you need to multiply this with the total capacity, no? That's your time, T sub T. Okay, so that's how you're going to calculate the saturation loading capacity. So you can start with 754. This would be equal to 754 cubic centimeter per second. Okay, just multiply this with density 0.00115. This is in grams per cubic centimeter. No? Of course, this is air. This is still air. We're speaking of air. Remember, our process is we're trying to remove alcohol from air. So this density is of air, and then this flow rate is for air. No? Tapos, we're going to use the given concentration. The concentration is 600 ppm or parts per million. So times 600, for every 600 grams of alcohol, 600 ppm, there will be 1 million, 1 times 10 to the 6 grams of air. So that's how I interpret 600 ppm. So this will give you the grams of alcohol. So take note, ano? Grams of alcohol per second. This is grams of alcohol per second. Pero remember, in order for the column to be saturated with alcohol, you need to use it for T sub T. And then T sub T is, I think it's 5 point something hours. Ano? 5.28 hours. So you need to use it for 5.28. Nang mag-work ng pen, Karen, and text. Makanulat ko dito. Yung nawala.
Baka kailan mo balikan?
Okay? So multiply this with 5.28 hours. And then convert this to seconds. So that would be times 3,600 seconds per hour. So, of course, I hope you can see the cancellation of units. So, matitira na lang dyan is grams of alcohol. And then finally, divide this with the grams of carbon, which is 79.2 grams of carbon. So, this would be 0.125. 0.125. So, this is the saturation loading capacity. Grams of alcohol per grams of carbon. Okay? So I hope you understand the calculation. Let me go back to the PowerPoint. Okay. So this part is so for example, you wanted to produce a new column with a higher capacity. So how are you going to design the new column? What will be the new length? So if the breakpoint time required for a new column is 6.0 R, what is the new total length of the column required? So basically, you're just going to use this equation. H B tall divided by TB tall. Okay, this is given. This is the 6 R's, TB tall, is equal to H. We're using capital H. Ano? Capital H. Supposed to be capital H. HB small divided by TB small. So if you still remember, we have these two values, HB small and TB small. We have solved this in our initial calculations. Tapos TB tall is now 6 hours. The new breakpoint time is now 6 hours. So what we're going to do is we're going to calculate HB tall, and then we're just going to add the HUNB, and then we have the new total length of the column. Ganun lang, ano? So HB tall divided by TB tall. So the value of TB tall is 6 hours. It's given in the problem, 6.0 hours. HB small, you can review this if you're not taking down notes. So HB small is 9.65 centimeter. And then TB small is 3.64 hours. Okay, so you should be able to calculate HB tall. This should be 15.91 centimeter. And then you basically just add the HUNB. So the total height, the new total height is HB plus HUNB. Remember, HUNB is constant, whether the column is small or short. So HB tall is 15.91 centimeter plus HUNB. HUNB is 4.35 centimeter. Okay? So that's the practical use of HUNB when you're scaling up. So something like 20.26 centimeter. So this is the designed height of the new column for the new capacity. So I hope you understand this solution. Okay, so with this, we're done with adsorption discussion. Next, I'm going to discuss membrane separation. So that would be the last unit operation for CHE134P that would be included in our final exam. So see you on the next video.